morning, friends. I wish you have started to study or to learn how to plot shear force and bending moment diagram. So in the same series, today we are going ahead, that is the shear force and bending moment diagram for overhanging beam. So in today's session, we will learn the concept of shear force and bending moment. We are able to plot the shear force and bending moment diagram for overhanging beam, as well as to understand the relationship between shear force and bending moment. Before we will proceed further about how to plot the shear force and bending moment diagram for an overhanging beam with the different loading conditions, let us revise about shear force and bending moment. Let us clear out our fundamentals. So, what is shear force and bending moment? When a beam is loaded by forces or couples, stresses and strains are created throughout the interior of the beam. These internal quantities are referred as shear force and bending moment. Let us be understood by using the simple beam. This is a given beam with application of external loading. Now, when I will cut this beam at any section, my beam will be divided into two parts, left part and right part. When we will study the individual free body diagram of the left part, it will be seen over here. This left part, see this section, the section is subjected to these internal quantities. These internal quantities is referred as shear force and bending moment. Now, our intention is in this series is to find out these internal quantities for three different kinds of beam: simply supported beam, cantilever beam and overhanging beam, with the application of external loads in terms of point load, uniformly distributed load, uniformly varying load and couple. Now next, how the shear force will be defined? Shear force is the algebraic sum of all the vertical forces acting to the left or right of a cut section along the span of the beam. It is interesting point is algebraic sum of all the vertical forces, maybe on the left side, maybe on the right side. Similarly, the bending moment is defined as the algebraic sum of all the moment of forces to the left or right of the section. Interesting point is algebraic sum of all the moment of the forces to be referred as bending moment. Let us study, or let us revise, or let us make ourselves to be clear, fundamental, what is the sign convention of a shear force and bending moment. A beam is given to us, and let us cut a beam over here. So my beam will be divided into two parts, left part and the right part. Now for section left part, if my shear force is of upward, or section right part, the shear force which is acting downward, this sign convention is treated as positive shear force. In opposite to that, if a section left part subjected to the downward shear force or section right part subjected to the upward shear force, treated as negative shear. For bending moment, section left part subjected to clockwise moment or section right part subjected to anti-clockwise moment, this generates sagging nature of bending moment, referred as positive bending moment. Vice versa, section left part anti-clockwise moment or section right part clockwise moment, this is referred as negative moment. Maybe it is also be referred as Yes, please repeat. It is to be referred as hogging bending moment. And this hogging bending moment is treated as negative bending moment, and this is general, which I have been used thoroughly in this the whole series, the sign conventions. You may change the sign convention, maybe plus or minus sign depending upon your convenience. Now, how to find out the shear force and bending moment using the static equilibrium approach? This is the steps of the procedure. The step number 1 is to determination of the reactions. We have to cut the beam at a certain cross section, and we have to draw free body diagram of one piece of beam. We have to set up the equilibrium equations. We have to solve for the shear force and bending moment at the cross section, and then we have to plot the shear force and bending moment diagrams. Let us be understood by taking this particular problem. Now, in the previous last 2 lectures, we have solved a problem of overhanging beam with the UDL as well as point load. So now in the today's session, let us take the next third load we are incorporating, that is the uniformly varying load. Please refer in this particular figure. Overhanging beam, this span of 1 meter which is overhang or which is beyond this support, so it is a one-way overhanging beam subjected to a uniformly distributed load up to 4 meter, and then it is subjected to the 60 kilonewton point load at the free end at the tip of an overhanging beam. And our intention is to find out the shear force and bending moment at each and every section, and then we have to plot the shear force and bending moment diagram. Question may arise, how to plot? Step number 1, we have to find out first reaction, support reaction. Visualize, this is my support A. My support A, which is subjected to, it is a name of the support is hinge support, so having a 2 reaction, horizontal reaction as well as vertical reaction, while B support, which is a roller support, hence it is subjected to a single reaction, that is a vertical reaction. So here in this particular beam there are 3 reactions, horizontal and this 2 vertical, 3 reactions, and first our step number 1 is to find out the support reaction. Let us find out the support reaction. Before we found out the support reaction, let us we make a revised figure and let we did the equivalent point load. What we did right now, we converted this uniformly varying load in terms of equivalent point load, because the load which is of the triangular nature, which is converted in terms of equivalent point load as the area of triangle half into 20 into 4, which is subjected the CG of the triangle. Now question may arise, what is the CG of triangle? That is, from this side it is the 2/3 of total distance, and from this side is 1/3 of total distance. So as for that, the total distance of 4 meter, so from this A point this is of 2/3 of 4. That is the application of the equivalent point load. So now let us find out the support reaction. Step number 1, sigma h is equal to 0. Now refer this previous figure. Here all the external loads are of vertical nature. So this load is only the horizontal load which is acting on this particular system, hence RAH is equal to 0. That we achieve over here. Refer, RAH is equal to 0. Now let us use the second equilibrium condition, sigma V is equal to 0. Refer the figure. When we will take the sigma V is equal to 0, sigma is the symbolic representation of summation. V is nothing but the vertical forces. So sigma V is the sum of all the vertical forces. Please refer this figure carefully. By referring this figure, sigma V is equal to 0, upward. We are assuming to find out the reaction, upward is positive. So RAV is upward. So plus RAV minus this equivalent point load minus half into 20 into 4 plus RB minus 60 into 0, and we achieve equation RAV plus RB is equal to 100 kilonewton. The thing which is over here to note down that this sigma V is equal to 0 gave us an equation which is consisting of combination of RAV and RB. Now our intention is right now is to find out the individual value of RAV and RB, and for that we have to use the third equilibrium condition, that is sigma M is equal to 0 at any point. It is important for us either you take maybe at support A or maybe at B or any other point, and you have to take the moment of all the forces. As for that, if we take sigma MA is equal to 0, that is the summation of all the moment of forces at A which is equated with 0, then please refer the figure. We have to take the moment of all the forces over here. Now when we are taking the moment of all the forces, then RAH which is acting at A, and obviously the RAH itself is 0, the moment because of RAH is 0. But RAV which is acting at A point, and we are taking the moment at A, so we do not have any kind of perpendicular distance, because we know that the moment is nothing but the force into perpendicular distance. So RAV into 0 which is 0, so this force and its moment is nullified by taking the moment at A. Now another force is this equivalent point load, that is half into 20 into 4, it is the load of force multiplied by perpendicular distance, that is 2/3 of 4 from A. So half into 20 into 4 into 2/3 into 4, this creates clockwise moment at A, hence it is treated as positive. Now this RB into perpendicular distance is 4, RB into 4 creates anti-clockwise moment, hence treated as negative, so minus RB into 4. Now this 60 into total distance from here to A, so 4 plus 1 5, so 60 into 5 creates the clockwise moment which is equal to 0. So we have the three forces and its moment which has been taken care while taking the moment at A. So now please look it out over here. The same equation, half into 20 into 4 into 2/3 into 4 minus RB into 4 plus 60 into 5 which is equal to 0, and we get RB is equal to 101.67 kilonewton. So once we know the value of RB, we have to put this value of RB in this equation. Then we got RAV is equal to 100 minus 100, 1.67 is equal to minus 1.67. Please be careful, this minus sign. Minus sign indicated that, refer the previous figure, minus sign indicated that the direction in which we over here assumed as upward, which is false, which is wrong. It is truly negative, means this force which is, or this reaction which is acting downward. So RAV is equal to 1.67, but which is of downward direction. Same reactions you can alternatively found out by taking the sigma MB is equal to 0. You may take care, you will learn this by taking alternative approach also. So once we found out this moment, once we found out these forces, our next step is to plot shear force and bending moment diagram. So let us go to the tabletop over here. Now the given beam, which is of overhanging beam, kilonewton per meter, this is of 60 kilonewton, length of 4 meter, length of 1 meter. this beam which has been given to us, and RB, this is A section, this is B section, this is 101.67, and this is downward direction acting 1.67, and our intention is to plot the shear force and bending moment diagram. Now let us reuse our concept, and what happens we will visualize. Shear force at A is equal to, now see, this is acting downward, so 1.67. If we take a section over here, section left downward tilted is negative, so we got shear force at A is minus 1.67, and all the minus sign we have to plot below the baseline. Now shear force at B is equal to, we have to find out over here. My intention is to find out what is the shear force at B. Minus 1.67 plus half into 20 into 4, and that we achieve is of, this is also acting downwards, so instead of plus sign it is of minus sign. Section left acting downward, and we got minus 41.67, so we achieve over here 41.67 minus sign. How to join these 2 points? Should I join with the parabola? Should I join with the straight line? Which kind of parabola? That we do not know right now. It means that, should I join these 2 points with this straight line? It obviously no, as we know that the given load is of UVL. Should I join by this kind of parabola? Should I join with this kind of parabola? Which parabola I have to adopt? Should I go for number 1? Should I go for number 2? Should I go for number